The normal distribution as a model for measurement. Example 1 says the life expectancy of a particular brand of light bulbs is normally distributed with a mean of 1,500 hours and a standard deviation of 75 hours. Draw an appropriate normal curve showing the z-score below. So you would have your line, you'd have your normal curve. It tells you that you have a mean of 1,500 hours, so in the center you'd have 1,500. And then it tells you have a standard deviation of 75 hours. So on this side you have one standard deviation, which would be at 1,575. Two standard deviations, which would be at 1,575 plus maybe 75, and that would give you 1,650. And then you'd have 1,650 plus 1,725. On the other side, you would need to subtract 75. So 1,500 minus 75 would be 1,425. $1,425 minus 75 would be $1,350. And $1,350 minus 75 would be $1,275. So if you wanted to, underneath that, it might be helpful for you to say this is 3 standard deviations, this is 2, this is 1, 0, because that's the mean. This would be -1, this would be -2, and this would be -3. So the top numbers up here represent the hours, but then the bottom numbers down here represent the z-scores. A says what is the probability that a light bulb will last less than 10 hours. So for this one, you could figure out what the z-score was by doing your 1,410 minus the mean, which is 1,500, divided by the standard deviation, which is 75. So remember that to find your z-score, you would do x minus the mean over the standard deviation. So whenever you do that, you would get -1.2. So we would be looking for the value to the left of this right here. So we could use the standard normal table and look for -1.2. and see what the probability was that way. Or we could do this on the calculator. If you do this on the calculator, you're going to use normal CDF. Where your lower bound is negative 1e99, so negative infinity. Your upper bound would be your 1,410 hours. You could put your standard deviation and your mean based on the problem. So your mean would be 1,500 and your standard deviation 75. So whenever you go to do this on the calculator, you would do stat, you would do calc, you would do, just kidding, you do second bars, you would do normal CDF, where your lower bound is negative 1e99, your upper bound is 1,410, your mean is 1,500, and your standard deviation is 75. So whenever you do that, you would get 0.115, we'll round it to 1. So 0.1151. What is the probability the light bulb will last between 1,563 and 1,648 hours? So for this one, we can do normal CDF again. This time our lower bound is 1563. Our upper bound is 1648. Our mean stays 1,500. And our standard deviation stays 75. So you would go to the calculator, do second bars, normal CDF. Lower bound this time is 1563. Your upper bound would be 1648. Mean and standard deviation are going to stay the same. And whenever you do that, you would get 0.1762. C says, what is the probability the light bulb will last between 1,416 and 1,677 hours? So you would do this one the same way, so normal CDF. Your lower bound is 1416, your upper bound is 1677, your mean is 1500, your standard deviation is 75. So on the calculator, second bars, normal CDF, your lower bound 1416, your upper bound 1677, mean and standard deviation would stay the same. Whenever you do that, you would get 0.8595. Number 2 says a packing machine is set to fill a cardboard box with a mean of 16.1 ounces of cereal. Suppose the amounts per box form a normal distribution with a standard deviation equal to 0.04 ounces. Draw an appropriate normal curve showing the z-score below. So you would have your curve. Your mean would be in the middle at 16.1. You've got a standard deviation of 0.04. So 1 would be 16.14. 2 standard deviations would be 16.18, and 3 would be 16.22. One away on the left would be 16.06. 2 would be 16.02. And 3 would be 15.98. So this represents ounces of cereal. This below is going to be the z-score. So in the middle we would have 0. For 16.41, that was 1 standard deviation away. For 16.18, that's 2. And for 16.22, that's 3. Remember that the z-score is just is really just how many standard deviations you are away. So 16.06 would be -1 because it's -1 standard deviation away. It's below 1 standard deviation. That would be -2 for 16.02, and 15.98 would be -3. A says, what percentage of the boxes will end up with at least 1 pound of cereal? Alright, so for this one you got to know that 1 pound is 16 ounces. So you got to have at least 16 ounces of cereal. So to do this one, you would do normal CDF this time. And you are basically going to say if it's going to have at least 16 ounces, then that means that 16 is going to be your lower bound, and your upper bound would be as high as it could go. So 1E99 for positive infinity. Your standard deviation is 16.10, or your mean is 16.10, and your standard deviation is 0.04. So on your calculator, second bars, normal CDF, your lower bound is 16, your upper bound is 1E99, your mean is 16.1, and your standard deviation is 0.04. So that gives you 0.993, we'll say 8. So 0.9938. 10% of the boxes will contain less than what number of ounces? So for this one, you're actually going to go kind of backwards. So you are going to be looking for, if you were thinking about this visually, you'd have your standard normal. You would be looking for 10%. So where the area is equal to 0.1, and anything less than that. So you're looking for this over here. So anytime it gives you the percent, you're going to use inverse normal to figure out what the z would be. So to do that, your lower bound would be 0.1, or excuse me, your area would be 0.1, your mean would be 16.1, and your standard deviation would be 0 or 0.04. So on your calculator, you do second bars. You're going to do inverse normal, which is 3. Area is going to be 0.1. Mean is going to be 16.1. And standard deviation is going to be 0.04. So whenever you do that, you get 16.049. So 10% of the boxes will contain less than 16.09 ounces. C says 80% of the boxes will contain more than what number of ounces? Alright, so for this one, you're trying to find your line. Your area over here is 0.8. Because it says 80% of the boxes will contain more than what number of ounces, you're going to be looking for when the area over to the right is 0.8. Remember that your z-scores and your normal CDF give you the area to the left. You need to the right for this one, which means you're going to have to do a little bit of work. If this is 0.8 over here, that means that this right here is 0.2. So to do this one on the calculator, you're going to do inverse normal. You are really trying to find, really, even though these questions are asking you two different things, they're really not. Because this one is saying they're going to contain less than what number. So this being your line. And this one is asking you for this number as well, but this time 80% are going to contain more than what number of ounces. So really, instead of you being worried about the 0.8, you're really going to be worried about the 0.2. So when you plug in your area here, it's going to be 0.2. Your mean is still going to be 16.1. Your standard deviation is 0.04. So whenever you plug it into the calculator, do second vars, inverse normal. Your area this time is 0.2. Your mean and your standard deviation are not going to change. Whenever you do that, you get 16.066. So we'll call it 16.07. D says the middle 90% of the boxes will be between what two weights? So if you have this, the middle 90% means that you are looking for this. This is what you have. So you are trying to find here and here your lines. So the area here would be 5%, and the area here would also be 5%, because altogether it's going to give you 100%. Alright, so what you can do is you're going to split this up and actually do two different steps on your calculator. So you're going to find inverse normal when you do this area as being 0.05. So this area with your mean at 16.1, your standard deviation still at 0.04. So second vars inverse normal 0.05, mean and standard deviation are going to stay the same. And whenever you do that, you get 16.03. Then you're going to do inverse normal where now you're going to use this line. So if you use this line, below that line would be 90 and then another 5, so 95%. So 0.95, mean is still 16.1, standard deviation is still 0.04. Second bars, inverse normal, 0.95 this time, mean and standard deviation stay, and you get 16.165. So we'll do 16.17. So that means that you have to be between 16.03 and 16.17. Commonly used probabilities and z-scores. So 90% of the values are between z-scores of negative 1.645 and positive 1.645. 95% of the values are between z-scores of negative 1.96 and positive 1.96. 99% of the values are between z-scores of negative 2.576 and 2.5 positive 76. 68.26% of the values are between z-scores of negative 1 and positive 1. 95.44% of the values are between z-scores of negative 2 and positive 2. And 99.74% of the values are between z-scores of negative 3 and positive 3. 3 says, suppose the average height of male adults in a particular locality is 70 inches with a standard deviation of 2.5 inches. If the distribution is normal, the middle 95% of males are between what two heights? Alright, so your critical values, or your critical z-scores from up here, tell you that 95% of the values are between z-scores of negative 1.96 and positive 1.96. So remember that z-scores are just how many standard deviations away you are from the mean. So if you have a mean of 70 inches, you would basically do 70 plus or minus your standard deviation, which is 2.5, times the z-scores that are associated with 95%, which would be 1.96. So whenever you do that, that really is 70 plus or minus 4.9. So you should get two answers. 65.1 on the low end, so when you do 70 minus 4.9, and 74.9 on the high end, so when you do 70 plus 4.9. 90% of the heights are below what value? Alright, so for 90% of the heights are below what value, it's important that you know that 90% of the values are going to be below a z-score of 1.282. So here we have listed the ones that are between. So for below, 90% is associated with 1.282. 95% is associated with 1.645, and these are the z-scores. And then 99% are below a z-score of 2.326. For above, 90% of the values are going to be above a z-score of negative 1.282. Above a z-score of negative 1.645 for 95%. And for 99%, they're going to be above a z-score of negative 2.326. So B says 90% of the heights are below what value? That would be below 1.282 standard deviations away from the mean. So for this one, you would do 70 plus 2.282 times the standard deviation, which is 2.5. So whenever you do that, you get 73.205. C says 99% of the heights are above what value? So for above, that's going to be negative 2.326 z-score. So you would do 70 minus 2.326 times the standard deviation, which would be equal to 64.185. D says what percentage of heights are between z-scores of plus or minus 1, plus or minus 2, plus or minus 3. So plus or minus 1 would be 68.26% here. 2 would be 95.44%. And plus or minus 3 would be 99.74%. And these are all respectively. Finding means and standard deviation. So if we know that a distribution is normal, we can calculate the mean, which is mu, and the standard deviation, which is sigma, using the percentage information from population. So given a normal distribution with a mean of 25, what is the standard deviation if 18% of the values are above 29? So if they have a standard deviation, or we're trying to figure out what the standard deviation is, but it tells us that 18% of the values are above 18% of the values are above 29. That means that 82% are below 29. Alright, so if you looked on the standard normal table and you were looking for 0.82 in the bulk of the table, then you would find that the corresponding z-score would be equal to 0.92. So what that means is 29, which is the value that we are looking at, our x value, minus our mean over our standard deviation would be equal to 0.92. So what that really means is we could multiply both sides by sigma. So we would have 29 minus 25, which is 4, equals 0.92 times sigma. Divide both sides by 0.92, and that would tell you what sigma was, which is your standard deviation. So your sigma would be 4.35. Example 5 says, given a normal distribution with a standard deviation of 19, what is the mean if 21% of the values are below 50? Alright, so what you could do is 21% the same thing as 0.21. So you're going to go to your standard normal table and look for 0.21 in the bulk of the table. So whenever you do that, you should get a z-score that is equal to negative 0.81. Now, because it's asking us for the mean, that means that we can basically say we're looking for the mean, but we're talking about 50. So we can say 50 is negative 0.81 standard deviations from the mean. Therefore, the mean would be equal to 50 plus 0.81 times 10, because it tells us a standard deviation of 10. Not 10, 19. It's literally 2. I wish you could see this clock. It's 2 o'clock in the morning and I'm losing my mind. Alright, so whenever you do this, you get 50 plus 0.81 times 19. So you should get 65.39. 6 says, given a normal distribution with 80% of the values above 125 and 90% of the values above 110, what are the mean and the standard deviation? So you need to look at the standard normal table for 0.8 and 0.9. And so whenever you do that, that would give you z-scores. That would be negative 0.84 and negative 1.28. So what that means is, for the first one, 125 minus whatever the mean is over the standard deviation is equal to negative 0.84. For the other one, 110 minus whatever the mean is over the standard deviation, whatever that is equal to negative 1.28. So now you could say, I'm going to have to work this out over here. You could say 125 minus the mean equals negative 0.84 times the standard deviation. And 110 minus the mean equals negative 1.28 times the standard deviation. You could divide this one by negative 0.84. So that would give you sigma equals 125 minus the mean over negative 0.84. Over here, you could divide by negative 1.28 to get sigma by itself. And whenever you do that, you get sigma equals 110 minus mean over negative 1.28. Now, because these both are equal to sigma, that means that I could set these two things equal to each other. So 125 minus the mean over negative 0.84 equals 110 minus the mean over negative 1.28. So you could cross multiply. Because you've got two fractions that equal to each other. So you could say 125 times oh no, I lost it. Times negative 1.28 is negative 160 plus 1.28 times the mean, and then you could do negative 0.84 times 110, and that gives you negative 92.4, and then plus 0.84 m. So then let's combine our like terms. So we would have 1.28 times the mu minus 0.84 mu equals negative 92.4 plus 160. So you'd say 1.28 plus, minus 0.84 gives you 0.44 equals negative 92.4 plus 160. Which is 67.6. And then divide that by the 0.44. And whenever you do that, you get a mean of 153.64. It's a lot of work in a tiny space. Alright, so then you could plug back into either one of these to figure out what your sigma is. And your sigma for this particular problem would be 34.09. Alright, normal approximation to the binomial. So many practical applications of binomial involve examples in which n is large. However, for large n binomial probabilities, this can be quite tedious to calculate. Since the normal can be viewed as a limiting case of the binomial, it is natural to use the normal to approximate the binomial in appropriate situations. The binomial takes values only at integers, while the normal is continuous with probabilities corresponding to areas over intervals. Therefore, we should establish a technique for converting from one distribution to the other. For approximation purposes, we do as follows. Each binomial probability corresponds to the normal probability over a unit interval centered at the desired value. Thus, for example, to approximate the binomial probability of 8 successes, we determine the normal probability of being between 7.5 and 8.5. So example 7 says, suppose that 15% of the cars coming, off an assembly plant have some defect. In a delivery of 40 cars, what is the probability that exactly 5 cars have defects? Alright, so for this one, you can do binomial PDF. And we can do binomial PDF because it says exactly. So binomial PDF, where the number that you were looking for is 40, 15%, and 5. So whenever you do that, you should get 0.1692. Example 8 says, if 60% of the population support massive federal budget cuts, what is the probability that in a survey of 250 people, at most 155 people support such cuts? Alright, so this one says at most, so because it says at most, I can do binomial CDF. 250 is the number of people that you surveyed. 60% support the federal budget cuts. And then we're looking for at most 155. So whenever you do that, you should get 0.7605. For checking normality, normal is a good approximation to the binomial whenever both np and n times 1 minus p are greater than 10. The initial check should be to draw a picture. Dot plots, stem plots, box plots, and histograms are all useful graphical displays to show that data is unimodal and roughly symmetric. Example 9. So the ages at inauguration of U.S. presidents from Washington to George W. Bush were, and then it gives you the ages. Can we conclude that the distribution is roughly normal? So what you could do is you could plug all these in to your calculator and let your calculator draw the picture for you. So go into the calculator, you can go to Stat, go to Edit, clear out anything that's in L1, and then type in your new values using the numbers that were given to you in set. Once you finally get all of that typed in, which could potentially take you the rest of your life, then you're going to go to second y equals and turn the stat plot on. So whenever you get here, you are going to go to enter, and then you can turn it on, and then choose whichever of the distributions that you like. So I'm going to go with histogram, Whenever you do that, your X list shows up as L1, and then you can hit graph. Oh, I got something in Y equals. Hold on. So then always hit zoom, and then stat, and then you can see your distribution. So as you look at this distribution, you can tell that it's roughly unimodal. So unimodal meaning it just has 1 point, and it's roughly symmetric as well. So because it is roughly symmetric and unimodal, then we can say yes. A more specialized graphical display to check normality is a normal probability plot. When the data distribution is roughly normal, the plot is roughly a diagonal straight line. This is not easy to calculate by hand, but can be done on the calculator. So what you're going to do is once you get everything typed in, you can go to stat plot. So second y equals, and then hit enter so that you're on stat plot 1, and you're going to go to the sixth distribution. So 1, 2, 3, 4, 5, 6. So when you go to type, go all the way over, and then hit enter. All that's good. So then graph. So this is the normal probability plot. So as we look at it, if you see that it is kind of a diagonal straight line, then that means that your distribution is very close to normal. So as we look at this, we can tell that it's definitely a line. It's pretty straight, and we can tell that it's definitely diagonal. So that's another way that we could see that it was close to being normal.